Hello and welcome back. In this lecture, we learn about the concept surface tension. Surface tension is another fluid property. To understand this concept, consider a small insect floating on the surface of the water. Another similar example is, if you place a razor blade gently on the surface of water, it will also float. Both these phenomenon are possible because of the fluid property, surface tension. In this lecture, we will discuss about this interesting fluid property. To better understand this concept, consider a fluid with free surface. A droplet of water will be a good example. If we look closely at two locations, one on the surface, and the other inside the drop, we can see that surface molecules experience an unbalanced intermolecular force or cohesive force, in comparison to a fluid molecule inside the droplet. A molecule inside the droplet is pulled equally from all directions, while a surface molecule experiences an unbalanced force towards the interior. The physical consequence of this unbalanced force is that the liquid-free surface will act as a hypothetical skin or membrane with tensile force acting on it. This tensile force acting at the surface per unit length is called surface tension. The surface tension is usually denoted by the symbol sigma. Consider a water drop. The pressure inside the drop is higher than the surrounding air. Let P1 is pressure in the surrounding and P2 is pressure inside the drop. Let the difference is delta P. To understand the relation between the delta P and surface tension of the fluid, consider a half section of the drop. A free body analysis will indicate that surface tension forces acting along the circumference of the drop is balanced by the pressure force acting on the circular area. Equating these two forces, we can derive an equation connecting delta P, radius of the bubble, and the surface tension of the fluid. Consider another example, a soap bubble. Essentially, a bubble forms when we blow air into it. Logically, we can conclude that the pressure inside the bubble is slightly higher than the surrounding air. Let P1 is pressure at the surrounding and P2 is pressure inside the bubble. Let the difference is delta P. This slightly higher pressure will try to increase the volume of the bubble, but it will be balanced by surface tension forces acting at the surface. To understand the relation between the delta P and surface tension of the bubble fluid, consider a half section of the bubble. A free body analysis will indicate that surface tension forces acting on two circumferences of the bubble is balanced by the pressure force acting on the circular area. Equating these two forces, we can derive an equation connecting delta P, radius of the bubble, and the surface tension of the fluid. Consider a water droplet of radius 2 mm at 20 degrees Celsius. The surface tension of water at this temperature is 0.007 Newton per meter. Calculate the pressure inside the drop. The atmospheric pressure is 101.3 kilopascals. In this problem we use the equation derived earlier, connecting pressures inside and outside the drop to its radius and surface tension. Substituting the given values of outside pressure, radius and surface tension, we can calculate the pressure inside the drop. It is slightly higher than outside pressure. Consider a soap bubble droplet of radius 60 mm. The surface tension of soapy water is 0.002 Newton per meter. Calculate the pressure difference across the bubble surface. In this problem, we use the equation derived earlier connecting pressures inside and outside the bubble to its radius and surface tension. Substituting the given values of outside pressure, radius and surface tension, we can calculate the pressure difference delta P across the bubble. It is slightly higher than the outside pressure. I hope you understand the concept surface tension. Thank you for listening.